Howdy. So I will just continue to talk about copper. I somehow tried to make this one video which explains everything, but I failed miserably. So then I tried to make it somehow a continuous video, and now I decided I just continue talking and still show more stuff which is related to the thing. We have been talking about the coat of arms of Outokumpu, and yellow for sulfur, red for the burned sulfur. We have the tridents, the thunderbolts, in other words, electrical discharge events. We have here on the lower left, maybe I have to change the color. On the lower left, here is the surface conductivity anomaly of Scandinavia. It's not visible here, but it says OKU, OKU, which is short for Outokumpu. Here on the right, we have the polar cusp reconnection, the apple, the torus, the magnetic field of Earth, magnetosphere. It somehow looks like that on the right side, and it has somehow similarities with the surface conductivity anomaly of Scandinavia. Here is yet another cusp reconnection. There is links to these pictures in the other videos, and I have personal proof because the picture of this aurora occurrence is made by me, myself, and it happened on the surface conductivity anomaly, whatever, polarity interface. They took the page down after I contacted them, so I just had a few screenshots. There would be a whole lot of text about the whole thing, but it's gone. Anyway, there was a surprise geomagnetic storm last year. There was auroras, and I noticed that, yeah, we are actually at this interface, which was very interesting. I mean, how many people are aware of such a thing? But yeah, I live here, and that's it. Yeah. You live here. Check it out. I have been talking about volcanic plasma. Geoplasma. I don't know what this should be called. Maybe volcanic plasma phenomena, a type of geoplasma. That's a screenshot from the Fuego volcano in Guatemala. And it's very nice to have all these things in one picture. There's volcanic plasma on the left, we have the eruption plume, we have Venus and Jupiter in the background. I have been talking about Birkeland currents. Yeah, I just gathered some pictures. They're not in the proper alignment, so they might jump from theme to theme. But anyway, iron, silica in the center, magnesium or manganese, maybe magnesium, I don't know. But we also have H and O on the outer side, hydrogen and oxygen. We come back to this later. The surface conductivity anomaly also has, in a way, the shape of some geological features on Earth and on Mars, the Valles Marineris. And in a way, you can also probably see Florida in Scandinavia. I've been talking about, I'm like since a very long time, no, maybe, I don't know, 2 years or something, that volcanic ash plumes could be antennas. In other words, the energy would go into the volcano as well, not only coming out. And here we have a lightning strike, which very obviously starts from this plume here, because it gets dimmer as farther away it gets, and then it starts to split. And here is also the very first moment where the lightning strike starts to ignite from. I made a video about this. It also relates to solar activity. And that's again Fuego, with some very nice plasma phenomena beside it. I made videos about this. But they're all related. That's the lightning strike which emerged from the ash plume of the volcano. Global electric circuitry. Ionospheric potential. Many other things. No, we are the same. We are electromagnetic beings. We had the tridents in the beginning in the coat of arms of Outokumpu. This is from Kalevala, Lemminkainen, and he has also a trident. As does he. Who was he again? Apollo? No. Craters? That's probably, I don't remember. Maybe that's Finland. Just turned a little bit. And the upper side is from the plasma rock side, Kuhasalo. The left one is a picture made by me and somewhat similar thing from the laboratory in the USA. And this is just something in order to show some repetitive patterns. Kuhasalo, the plasma rock site in Finland on the left, and the Hudson Bay on the right from Google Earth. Yeah, it's not that well visible in a way on the left side, but that's a crater. It didn't fit the whole, like, there's missing parts, but it wasn't possible to make it better. But anyway, repetitive patterns. And I checked my last video, stopped with talking about this paper, Origin of Precambrian Copper Sulfides of the Outokumpu district, Finland. And you have to pay or be a part of some institution in order to get the full text. But we went through to what we have, so there shouldn't be any problem with that. Let me show you still some other papers. So obviously this place here seems to be rather special because we have so many things here. Diamonds, copper, surface conductivity anomalies, and tales from the ancient people, such as aurora touching the ground and burn things, kill people, stuff like that. It turned out that the Outokumpu type of copper ore is an own, in a way, special ore. It's just, I didn't knew that some days ago. The Outokumpu ore type includes both massive copper, zinc, and CO. Is it CO, cobalt? Maybe? I don't know. And disseminated nickel sulfide deposits. Yes, it is cobalt. Yeah, just had to look it up. But anyway, the ores are associated with a rock assemblage of serpentinites. I talked about these calcitic rocks, cherty quartzites, and black schists embedded in sedimentous microgneiss. The Outokumpu CuZnCO deposit is predominantly pyritic, whereas the others are predominantly pyrothetic. For me, if there is this pyr in the beginning, it is related to heat, like the pyroman. So these are very basic, simple hints for whatever mineral you're talking about. If there's a pyr or something, there might be a very, very, very good chance that the thing got created with a very lot of heat because of its name, or the beginning of the name. Like pyrite, it needs heat and very, much energy in order to get it done. The ores primarily deposited by seafloor hydrothermal processes, but were deformed by a thrust which upgraded the primarily thin bed into thick, massive plates upgraded. Hydrothermal processes. As I have shown, there is not too much going on in terms of geothermal activity in Finland. Yeah, maybe in the past it has been different, but nonetheless, the moho is very deep. The exceptional mineralogical and chemical composition with abundant chrome silicates are the result of metamorphism in middle amphibolite facies of a hydrothermal deposit associated with ultramafics. Metamorphism. But they don't probably tell about the metamorphism. Or if they talk about it, there is one or two words which you're never gonna hear, which is electricity and magnetics. During the past decades of mining in Outokumpu, a number of ideas have been presented concerning the origin and type of the Outokumpu ore. Yeah, so I'm not the first one who tried to figure out how the copper got there. These ideas reflect not only the progress made in direct observations at the mines, but also changes in general or geological conceptions in different periods. Yes, I have been there. I saw red rocks. I made red rocks with my microwave. Yeah, I'm a simple man. I like simple things. Based on the epigenetic character noted in the contact relations of the ore, early models took various intrusive rocks, such as the Marianvara granite. Yeah, that's a very interesting place. Serpentinite. Again, I have been talking about the serpent of creation, which is Venus. But also that it not only might have been Venus, like we don't know what happens before we found the petroglyphs, like, you know, dinosaurs didn't write anything down, stuff like that. So these kind of things might have happened in the past many times, you know. Based, this we already have. Serpentinite and a non-outcropping felsic intrusive rock. A non-outcropping. So there has been like the Marianvara. Vara again is a hill, like a kumpu. It's in a way the same thing. Hill. Or a mound. Or a fulgumite. A blister on Earth's first surface. As the parent rocks of the ore. Selective tectonic mobilization. Think about that. Selective tectonic mobilization. This implies to me that something was sorting stuff. Now, if you have metals involved, they probably react very easily to magnetic fields. And if there are really strong magnetic fields, of course, they gather at the strongest point of that magnetic field. This is how they get separated. And stuff which, like other things or sediments or how to, like, all those intermixed things, some gather just by their, like if you talk about boulders, small boulders fly much more far than a big boulder. And if the heat is sufficient enough, stuff might evaporate, stuff may transmutate, like the example about the sulfur. If there would be like a huge amount of sulfur in the air and there would be, you know, aurora borealis coming down very low, not even need to touch the ground, but the atmosphere in where we have all this sulfur, and they are really hot. And the sulfur burns and it turns red and it starts to rain, and it's raining red. Blood red. Yeah, because sulfur turns red when it gets heated. Okay? But anyway, selective tectonic mobilization. It seems that something was choosing particular things and moved them, and others, they weren't moved that much. Tectonics, or like if you push stuff together, like if you would play around with some miniature plate tectonics, like you would put stuff there on two plates, like sand, gravel, and then you just push them together. They wouldn't separate too much, they would just all get together. But we have here selective tectonic mobilization. The stuff was there and it got moved. Of the black schist sulfides was proposed by Saxela. Black. We have something which is black, so probably we have to assume that it's very burned. But anyway, basing his conclusions on the extensive descriptions by Bahatalo and Dissler, Borchert was the first author to propose a volcanic exhalative origin for the ore. I'm not aware of any volcano which would spit out copper or copper ore. If there's any, tell me, please. His idea was later supported and modified by Mäkelä, Gaal, Peltola, Mäkelä, Koisinen, Baus, Parkkinen, and Reino. The present paper is a review of the geology and classification of the Outokumpu ore deposits. Kereti, Outokumpu. Yeah, I'm not too far from that. I have been talking about like the surface conductivity anomaly interface area, which is not only in this kind of electronical way, like if you talk about the surface conductivity anomaly map, is something which is not somehow you cannot see it. If you go outside, you cannot see it. It's just on the computer, in the internet. Maybe someone has printed it. And actually, I did. But anyway, rocks geology, it's there. You can go to walk and check it out, watch it, cut it in half and polish it and watch and put it in the microwave. As I did. General characteristics of the rock types. The geology of the Outokumpu region has been extensively studied and in exploration conducted by Outokumpu Oy during the last 3 decades. According to available information, the copper ores of the Outokumpu region are related to a rock association of serpentinites, dolomites. Should I show? I have to show you that. Yeah, I really like him. I like how he's talking and all that stuff. It's a very sad thing that he has passed away, but Michael Steinbacher. Dolomite. Let's have just a quick listen to him.
These are welded tough, but on top of a lot of these mountains is dolomite. And dolomite's a big problem for geologists. If you Google dolomite problem, you'll get page after page of links. It doesn't form at the bottom of oceans the way geologists want it to. They need it to, but it doesn't do it according to chemists. They've tried to make dolomite precipitate out of ocean water. They can do it, but they have to boil it and fill the water with uric acid. So, picture dinosaurs urinating in a boiling ocean. 600 million years ago. And then that dolomite that can't happen is thrust up on top of mountains, like the Dolomites in Italy. The top of the mountains have the dolomite. It's almost like I wrote the reports about the dolomite myself. The beauty of dolomite is when they went to Comet Halley, they found 7% dolomite according to NASA, and they claim it's understated because it's tiny little crystals, microscopic, and their spectrometers miss a lot of it. So there's probably more. So you have comet dust that can answer the dolomite problem. All over the world you have this dolomite. It's my best friend. It's just the most wonderful stuff.
Yes, I will put a link below. I recommend you to watch it. Anyway, back to the paper. Dolomites, calcitic rocks, cherty quartzites, and black schists listed from the serpentinite core outwards. So now once again outwards, let's just draw a simple scheme of what we just read. Serpentinites, dolomites, calc-silicate rocks, quartzites, black schists listed from the serpentinite core outwards. So they are aligned away, they are separated. And if we take Birkeland currents into account, I won't now show you the Birkeland current simulator. Maybe should I? I have to. Yeah, this might be a very long thing to explain all those. The Birkeland current, which is basically a lightning strike, but much bigger. And here we are on the Birkeland current simulation or simulator site. And as you can see, the energy goes both ways. And it's rotating. In different directions at the same time. This could be the explanation of how and why those minerals are layered in the way they are. Because, as we just read, listed from the serpentinite core outwards. And the core, as they say, serpentinite, the dragon. The rock assemblage has been called the Outokumpu Association, and it meanders as a discontinuous band for up to 250 kilometers in the Karelian metasediments. The largest lenticular serpentine bodies may be as much as 10 kilometers long and 500 meters thick. Wherever the heterogeneous dolomite skarn quartzite envelope of the serpentinite bodies is isoclinically folded between tongues of serpentinite, it varies in thickness from a few meters to about 100 meters. The most continuous rock types are the black schist horizons. Again, black stuff, it might be very heavily burned, so very much energy was applied to the stuff there was, and probably new stuff came also from somewhere else. The Sun or Venus or something else, which mark the extension of the association, even if the serpentinites are lacking. Middle amphibolite facies metamorphism changed the mineral composition, and minerals such as cordierite, amphibolite, staurolite, andulosite, guyanite, and sillimanite indicate the highest PT conditions of metamorphism. So they were very heavily metamorphed. Polvijärvi. A zone of dolomite often occurs adjacent to serpentinite. As we know, plasma, or we have like this dendritical discharge pattern, like a lightning strikes, it's going to the side, like, like how a lightning strike looks. Anyway, and close to Talco's ultramafics in particular. They're talking about talc. Chrome diopside or chrome tremolite skarn, calc-silicate rock, is an intermediate member between ultramafics and quartzites where dolomite is absent. Banded skarn quartzite represents gradation to quartzite. Quartzite containing layers of dolomite. Skarn minerals, carbon chaos material, and sulfides in the banded metamorphic equivalent of the original chert horizon. Sulfur, sulfides. The color of the quartzite depends on the accessory minerals, pure quartzite being white, the sulfide bearing and carbon chaos varieties dark, and the chrome silicate bearing variety green. Yeah, remember my green stone? Chromite imparts a brownish hue. But yellow isn't mentioned, which is very interesting. Which would be sulfur. Calcareous, aggregaceous, and quartz-rich varieties of black schists are associated with the serpentinite quartzite assemblage. In the center of the Birkeland current, we have silica, quartz, the same thing. It depends just on the crystalline structure, or the absence of it. The amount of carbon chaos material is between 1 and 30%, with 5% as an average. The content of sulfides, pyrite, pyrrhotite, calciopyrite, and sphalerite varies in line with the carbon content. The contacts of the black schists against quartzites are sharp, a double layer, whereas there is gradation from black schists to mica gneiss. So it could be that black schists and mica gneiss is the same thing. That's why it's going gradation, like, it starts and the energy gets more, and we get from mica gneiss we get the black schist. But the other thing, there's a difference between, there's a double layer and something else happening. Maybe the magnetic field changed and some other material gets sucked into the place. But anyway, a characteristic feature of the Outokumpu assemblage is the abundance of a wide variety of chrome-bearing minerals in all the enveloping rock types. That calc-silicate rocks are green owing to chrome diopside, chrome tremolite, and uvarovite. Fuchsite and chromite are common accessories in the quartzite. Other chrome silicates are camerotite, tavmavite, chrome epidote, and chrome tourmaline. The chromite of the association is zinc-rich up to 9.6%, and also vanadium bearing up to 3%. Staurolite and garnet also contain zinc exceptionally. 0.4 to 0.87 zinc in staurolite and 0.62% in zinc in garnet. Granite and pegmative veins originating from the nearby Marianvara granite intersect the rocks of the Outokumpu assemblage and the ore bodies. Yeah, we have to watch this first. There's some pattern there. Serpentine pseudomorphs after metamorphic olivine in dolomitic host rock. Dolomite. I think I maybe talked about this already. But anyway, did I? But here on the right side, hanging wall contact of the massive ore with quartzite, scale bar 20 centimeters. The top here is black and the lower part is a little brighter. So it must have get burned very badly there on top of it, with heat which came from above and not below. Is Outokumpu a unique ore type? Yeah, the thing is, I made a video once about this and I deleted it. So now I don't really remember what I have been talking there and stuff like that. I'm a little bit confused about just this particular issue because I made a video about this already but didn't put it online. Now I really try to remember. I think I made a video about exactly these things. But anyway, let's go just a little bit on, because that's too interesting. I have been reading them many times because I tried to get a picture of the whole thing. So now let's just read it again if I did already. Current interpretations of the origins of the Outokumpu Association are based on long-term detailed geological, structural and petrographical analysis. The Outokumpu Association consists of ultramafic material from the mantle which erupted about 2.1 million years ago, or billion, or whatever this means, a long time ago, onto the bottom of the geosyncline, probably a back arc basin, and then intruded along the trench axis close to the bottom of the sea. Some of the igneous material extruded onto the seafloor. The heat flow associated with igneous activity resulted in hydrothermal processes on the seafloor, as a result of which the mantle-derived ultramafiite became hydrated and carbonated. Carbonate deposits and cherts precipitated from the hot hydrothermal fluids onto the ultramaphites erupted onto the seafloor. Simultaneously, sulfides were also deposited among the cherts. The sedimentary layering of the sulfides proves that they deposited from heavy saline solutions resembling those in present-day Red Sea deposits. Yeah, you know, salt is very conductive, only when it's in a liquid. The heavy solutions accumulated in the basins along the trench axis on the seafloor, and because of the topography of the floor, the Kereti and Vuonos ore bodies formed as independent occurrences. They're rather close. I have been showing these in other video. The hydrothermal activity caused by the igneous processes raised and led to increased biogenetic activity, of which the existence of black schists is a sign. The isotopic composition of the ore lead indicates no. The isotopic composition of the ore lead indicates a mantle origin if the plumbotectonics model is applied. Now, I've been reading about the plumbotectonics model, but we have lead. And I think it's so that if you would burn, let's say you have a huge amount of electricity, and you would burn uranium and stuff like that, you will get lead. And in the way, like watching at the whole thing with the electricity as the main force behind all this, and thinking about applying a huge amount of energy, because as I mentioned, there are uranium mines as well here in the same region. And if the after product of uranium is lead, after applying to it very much energy, then we just can assume that it's just a place where it got altered more. And probably also the magnetic properties change on all temperatures. But I think I leave it here. I try to continue from here, but I don't take too much pressure about that. I just want to share this stuff, and it's going to be shared the way it does. But that's also like, studying geology is studying petrified weather. Today there might be some possibility for thunderstorms also here, so now I need to be outside again and watch the clouds and do stuff in the garden, thinking about these and many other things. But anyway, thanks. Bye.